So normally when we think of quantum mechanics, we think of tiny subatomic particles which can be in these superposition states and fluctuating between different possibilities. But cosmology is the study of the entire universe, so there's this huge scale difference there. So Doddy, as a cosmologist, I was wondering, can you explain to me what on earth does quantum mechanics have to do with the universe?
Yeah, so the reason quantum mechanics can become important for the whole universe is because, as we've known since the time of Hubble, the universe is expanding, it's getting bigger. So if we know that the universe is expanding, we run the time back, the universe gets smaller. And as the universe gets smaller, all the atoms get closer together. At some stage, we'll have to consider atomic physics. When you get smaller again, you can encounter atomic nuclei. At some stage, you'll have to consider the quantum physics of nuclei. And then go back further still, we reach the limits of our knowledge. And this is where quantum mechanics and gravity are playing a role.
So can you tell us a little bit about the hard pieces of evidence that we have for the role of quantum mechanics in cosmology?
Yeah, so we actually know in a very precise way how to apply quantum mechanics to the whole universe, and at the same time as doing general relativity. And there's two key pieces of evidence for this. The first one is when we ask what was happening in the universe when it was only 3 minutes old. So when the universe was only 3 minutes old, it was a hot plasma like the sun. And what does the sun do? It burns hydrogen into helium and other heavier elements. The universe did just that. It burns hydrogen into helium and deuterium and lithium. And you can use the equations of quantum nuclear physics to predict how much, in particular, deuterium there should be in the universe. And astronomers have gone out and observed the universe, and they've worked out how much deuterium there is in it, and it's exactly given by the prediction from quantum nuclear physics in the first 3 minutes of the universe. And then the other thing comes from, okay, so the universe is very hot. It now starts cooling. It's a little bit older than 3 minutes. It gets to 100,000 years old. Now, at this point in the history of the universe, something dramatic happened, and it's called the formation of the cosmic microwave background. And what that gives us is a way to see a picture of the universe at this time, imprinted with all the quantum and plasma fluctuations on it. So what is the cosmic microwave background and how is it formed? We have to use quantum physics to talk about this. So as the universe cooled, it stopped being a plasma and it became transparent. And in order to work out when this happens and the temperature at which it happens, we have to solve the equations of atomic physics, the quantum physics of hydrogen, applied to the entire universe. And theoretical physicists did this in the early 20th century, and they were able to predict the temperature of the cosmic microwave background. And then later on, in the 1960s, this radiation was observed, microwave radiation across the whole sky, with exactly the temperature predicted by quantum physics.
So those are some of the known bits of quantum mechanics that work with cosmology. Obviously, there's lots of unsolved problems. I was wondering if you could talk a little bit about the more speculative aspects of this research.
Yeah, so as we run the universe back, when we go back beyond those first 3 minutes, when we go deeper than the physics of nuclei, we don't know what physics is at that scale anymore. And there's lots of speculative theories. So as you go back into the very early universe, you might be exciting all kinds of new degrees of freedom, new particles, new extra dimensions of space. If any of this stuff exists, it was all happening in the very early universe. And something that I'm interested in is how that then propagates forward into the physics of galaxies. So all the stuff that's created in this speculative early period of the universe, some of it survives and lives inside galaxies. It's something that we call dark matter. And that gives us a way to work out the physics that was happening in the very early universe. And in my research, that's related to exciting things like extra dimensions and string theory. And we can use the universe to tell us about that.
So altogether then, we know that quantum mechanics was important in the early universe. First of all, because it left this faint glow in the form of microwaves in the night sky that we can actually see, but then it also left a particular imprint in the form of light elements like deuterium, like you mentioned. But then if we go further back in time, things become a little bit more speculative, and there's lots of exciting research that's going on that we might actually be able to test for consequences for by looking in the hearts of galaxies.
Exactly.